Sarcopenic obesity, a dual burden of declining skeletal muscle mass and increased fat accumulation, presents one of the most challenging aspects of aging metabolism. As muscle tissue deteriorates and adiposity rises, mobility declines, metabolic rate drops, and risks of insulin resistance, frailty, and chronic disease escalate. At the heart of this imbalance lies the progressive failure of cellular maintenance pathways, particularly autophagy, which is crucial for preserving the structural and metabolic integrity of muscle. Nicotinamide mononucleotide (NMN), a NAD+ precursor known to restore metabolic resilience during aging, has shown increasing promise in stimulating autophagy in skeletal muscle. Through this mechanism, NMN may offer a multifaceted strategy to preserve lean mass and suppress fat gain in aging individuals. Skeletal muscle is a high-energy, mitochondria-rich tissue that requires constant quality control to remain functional. With age, impaired autophagy leads to the accumulation of damaged mitochondria, dysfunctional contractile proteins, and misfolded cytoskeletal components. This cellular debris contributes not only to muscle fiber atrophy, but also to increased oxidative stress and inflammation, conditions that further disrupt muscle protein synthesis and promote fat infiltration. By replenishing NAD+ levels, NMN activates key regulators of autophagy, including SIRT1, AMPK, and FOXO3A. These molecules converge to stimulate autophagosome formation, promote mitophagy, and facilitate the turnover of damaged cellular components, restoring a more youthful and efficient intracellular environment. NMN-induced activation of SIRT1 plays a central role in this restoration. SIRT1 deacetylates FOXO transcription factors, which upregulate genes involved in autophagy and muscle preservation, such as LC3, ATG7, and NIP3. At the same time, SIRT1 suppresses proatrophy genes like MUF1 and atrogen1, which are often elevated during muscle wasting. By reducing these catabolic signals while boosting autophagic clearance, NMN helps to maintain muscle fiber integrity, promote protein balance, and support the regenerative capacity of satellite cells, muscle stem cells that are essential for repair and growth. YMPK, another target of NMN-induced signaling, acts as an energy sensor in skeletal muscle. When activated, YMPK not only promotes fatty acid oxidation and mitochondrial biogenesis, but also enhances autophagy by inhibiting mTOR and activating ULK1. This ensures that in times of metabolic stress or aging-related decline, the muscle can clear defective mitochondria and proteins, restore its bioenergetic efficiency, and remain metabolically active. These cellular-level improvements are crucial for maintaining muscle mass and function in older adults. In addition to directly supporting muscle health, NMN's effects on skeletal muscle have systemic implications for fat regulation. Muscle tissue is a primary site for glucose disposal and lipid oxidation. When muscle mass deteriorates, metabolic flexibility is lost, leading to increased fat storage, especially visceral adiposity. By preserving or enhancing muscle mass through autophagy, NMN indirectly prevents this metabolic drift toward fat accumulation. Animal studies show that NMN supplementation improves insulin sensitivity and enhances the oxidative capacity of skeletal muscle fibers, shifting the balance from lipid storage to lipid utilization. In some aged models, NMN also reduces intramuscular fat infiltration, a hallmark of sarcopenic obesity, while improving endurance, mitochondrial density, and expression of slow-twitch oxidative muscle fibers. Moreover, NMN-stimulated autophagy may prevent chronic inflammation associated with muscle fat crosstalk in aging. Fatty infiltration into muscle releases pro-inflammatory cytokines like TNF-A and IL-6, which exacerbate muscle catabolism and reduce anabolic signaling. By improving cellular housekeeping and reducing oxidative stress within muscle cells, NMN lowers the inflammatory tone of the tissue microenvironment. This not only promotes healthier muscle but may also decrease spillover inflammation that contributes to systemic metabolic dysfunction and further fat gain. Although most of the current evidence is derived from preclinical studies, early human trials of NMN have reported improved muscle insulin sensitivity, better aerobic capacity, and enhanced endurance, all of which are indicative of improved muscle mitochondrial function and metabolic flexibility. These are promising proxies for preserved muscle mass and quality, suggesting that NMN may indeed have real-world utility in counteracting the metabolic decline seen in sarcopenic obesity. In essence, NMN-induced autophagy serves as a rejuvenation mechanism for aging muscle, allowing it to maintain structure, function, and metabolic activity. By clearing damaged proteins and mitochondria, supporting anabolic and oxidative pathways, and dampening inflammation, NMN may halt or even reverse the vicious cycle of muscle loss and fat accumulation that characterizes sarcopenic obesity. This restoration of muscle quality not only supports better movement and strength in older adults, but also recalibrates whole body metabolism toward a healthier, more balanced state. Through its effects on autophagy, NMN offers a compelling, multi-targeted intervention to preserve vitality and combat age-related metabolic decline at its muscular root.